Professor?
Yeah, Ivan, can you hear me at all?
Yeah. Is it coming from I think it's coming from the laptop. Hold on. Can you say again?
Yep, can you hear me all right?
Sorry, it seems as though your audio is only coming through the the laptop.
And not the speaker system?
Yeah, I don't know.
Do you want to try to log out and log back in to see if that changes anything?
Yeah, it might just be, yeah, let me just exit. Or actually, what is, okay, I'll leave and rejoin.
Okay.
Professor.
Yep, can you hear me now? Is there a way to adjust the speakers on like the caret button near the mute? Because that's where you select sort of your input and output on Zoom.
Professor, can you,
Yep, can you hear me now?
um, so you're on the laptop audio. I tried turning it up, but I don't know what the problem is.
On Zoom, on like the mute with the caret next to it, it should say like select a speaker. Is there anything there that you can change?
Yeah, so right now I'm on the laptop speaker, which is Realtek audio, and then the display audio is supposed to be the Extron Scalar D Intel R display audio.
Okay. Is there a phone number there for IT on the podium?
Um, is it CTS
Yes.
4 5?
Yes.
Is it the CTS
Yes. Could you just give them a call and see if they have any suggestions?
or the maybe it's sorry, is the IT the CTS?
Yeah, that's Classroom Technology Services. So can you give them a call and just ask them if there's something you should be doing different?
Professor,
Yep.
is IT the CTS phone number?
Yes. Yep.
Yes, so I'm having trouble with the setup at my lectures lectern with the speaker as well as the Logitech camera. What room is this?
Marcus 131.
Marcus 131. Yeah. Okay, thank you. Professor, can you speak again?
Yep, can you hear me at all?
Okay. So that was it. I didn't turn the projector on. My mistake. But the Logitech camera doesn't work, so the maintenance person is coming down.
Okay, so the audio is working, but the camera is not?
Yeah, the audio is working, what the camera is not.
Okay, so they can't see me yet? Is that what it is?
No, you can't see them.
Oh, well, that's okay. I don't know that that's as important.
Okay, do you just want to start? I'm sorry.
Yeah.
Okay. Sorry.
So that's okay. Why don't we just get rolling, and then when the tech people show up, you can just let them know that we got the audio working, so we got started.
Okay.
Okay, great. So hello, good morning. Sorry for the bumpy start, everybody. Never a dull moment with technology. So a couple quick announcements. So again, we are working through chapter 4, and tonight and Monday there will be a review based on critical points and inflection points. So if you want some extra practice or some help really thinking about local maxes, local mins, and inflection points, this will be a great review to go and do some practice problems. I emailed out the link. It's also posted in Moodle. Additionally, I sent out a class email today with instructions on how to calculate your current grade. This particular calculation is only accessible through Sunday when you take the next mini quiz, just because the values will change from there. So if you're interested in what your course average is right now, you should go ahead and calculate that, in the next couple of days to look at. So today we are going to talk about global maximums and global minimums, which is something I sort of alluded to when we started local maximums and local minimums. So I'm going to go ahead and switch over to the dot cam. Okay, so as a reminder, when we talked about local maximums and minimums, we said those happen at critical points. There can be more than one local max or local min, and they happen whenever we have a horizontal tangent line. So they are the highest and lowest points in a small space. Now, today we're going to talk about global maximums and global minimums. And in other textbooks, you might also hear these referred to as absolute maximums and absolute minimums. That's sort of the other way we talk about these. So a global maximum, a function is said to have a global maximum at P if f of P is greater than or equal to all values of f of x. So what that means is if there is a point on your function that is higher than all other points, that is your global maximum. So the highest point on your function. A function said to have a global minimum at P if f of P is less than or equal to all values of f of x. So one thing I want to talk about here is that when we talk about global maximums and minimums, we're thinking about these in terms of their y values, which is different than local maximums and minimums. So when we talk about the highest and lowest, we're talking about moving up and down the y-axis, okay? So let's look at this picture here and talk about where the global maximum and minimum would be. So the global maximum is going to be the highest point on the graph. So we're looking at all of the points for the entire function, and we're trying to figure out what is the highest one. Once we find that, we have our global maximum. And our global maximum is the Y value. So how high is that particular point? So we look at the Y value and we see that it's 2. So the global max value is 2. And again, this is different than local maximums and minimums, because for local maximums and minimums, we define them by their X value, so where they are. Global max and mins
The
are
audio
how
is
high or
fine.
how low.
I just didn't connect it to the I just didn't turn the HDMI on. Brain fart, but
Okay,
the Logitech camera doesn't work.
that's for.
All right. I'm just going to keep going. Hopefully this will all be okay. So to talk about the global minimum, we're going to do a similar thing where we're going to look at all of the points on our function, and we're going to find the lowest point. Okay, so down here, we have our global minimum.
That's correct.
Okay, so
And again, we're interested in the Y value. So we're approximating the Y value here.
plug it back.
It's about
in.
a third of the way, I would say here. So maybe 0.3, 0.4, something like that. But again, it's defined by the Y value. Now, when we talk about global extrema, which is what we call the global max and global min, we define them by their dependent value. So our functions will only have one or no global max or min, okay? However, it can happen at multiple places. So let's talk about these little cases here. So here we see a function that has one global max and one global min. Okay, let's talk about one that only has one of these. So let's say we have a function that looks like this, but has these arrows. So these arrows indicate that the two sides are going up forever. So in this scenario, this function has a global minimum, which is down here.
Thank you.
But no global maximum, right? So no global max. And the reason why it doesn't have a global max is because these functions go on forever and ever, as indicated by these arrows, okay? So here's a case where we don't have one of the two. Now, we can also have a situation where it happens at multiple places. So what does that mean? Okay, so let's say we have a function that looks like this, like a W shape, right? And in this scenario, let's assume that these are the same height, this and this, right? So we have a global minimum. And let's say that that global minimum is at -1. So we would say the global minimum is -1. It doesn't matter that it happens at two places. That is the lowest value that this takes on. And again, in this scenario, there's no global maximum because it goes on forever. So you can have a global value happen at multiple places, but you can only have one global value because it's the Y value, right? So if it's the same Y value at those places, then the global min is that Y value, okay? So how do we work with this? How do we find this? Well, leading up to our process here, I want to point out something on this first graph we looked at here. We've been talking about local maxes and mins. So if we were to draw in, these are our local mins. We also have a local max in the middle here. Okay, what I want you to notice is that this local minimum is also our global minimum, right? It can be both. And that our global maximum is at an end point, okay? Because it turns out that whenever you're looking for global points, these are the two places we are looking, okay? So let's look at our process here. So what you're doing with this, okay, starts with an assessment about whether or not you have endpoints. Most of the time, we do have endpoints. So we're going to start with this idea of what we do if we have endpoints. So in order to find global maximums and minimums on an interval that includes endpoints, so we're going to say that your function's between 5 and 10 or 0 and 30, right? What we do is we compare the values of the function, so those are the y values, at all of the critical points and all of the endpoints. The highest value from that list is our global max, and the lowest value from that list is our global minimum. So we'll come back to how we deal with things that don't have endpoints after we've practiced some endpoint problems, okay? So let's start with this example here. So example 1, find the global maximum and minimum of f of x equals x cubed minus 9x squared minus 48x plus 52 on the interval -5 to 11. So what you're going to want to do here is you're going to start by finding the first derivative, and we're going to use the first derivative to find the critical points of the function. Once we have the critical points, we're going to make a list, and that list will include the critical points as well as the two given endpoints, -5, 11, and then there's two critical points you'll find. So there'll be 4 numbers on your list. We're going to take all 4 of those numbers and plug them back into the original function to get the corresponding y value. Once we have the y values, the biggest one is going to be our global max, and the smallest one on a number line is going to be our global min. So I want you to try this out. I'm going to give you about 3 minutes. It's the first time we've tried it. So again, we're starting by finding critical points. So hopefully you're comfortable doing that now. Try it out, see what you can figure out. Even if you can't figure out all the pieces, hopefully you're comfortable with finding the first derivative and finding the critical point. And then, if that's as far as you get, fine. But if you are able to, then plug those points back into the original as well as the endpoints and see what you can figure out. Okay, so I'm going to give you about 3 minutes and then we will go through it together. Okay, take about 30 more seconds. All right. So again, our process here is we're interested in critical points and endpoints. We have our endpoints given in the problem. So we can actually put those right on our list to start with. So x equals -5, x equals 11. These are our endpoints. Okay. Now we also need critical points. So we know critical points are when the first derivative equals 0. So here, I take my first derivative, I'm going to get 3x squared minus 18x minus 48. And I want to know, when does that equal 0? I'm going to factor out a 3 first. And again, there's a couple different ways you can solve this. So if you didn't factor exactly the same way that I did, that is totally fine. So minus 6x minus 16. So then I'm going to factor this again. So x minus 8, x plus 2. Okay, so my critical points here, I have x equals 8 and x equals -2. Okay, you may have used the quadratic formula or factored differently, that's fine, but you should still get the same values for critical points. Now, there's one more step that I didn't talk about yet that is going to be important. And that step is checking your critical points to make sure that they are included in this interval. Okay, so we can only test points that are between -5 and 11. Fortunately for us, both of our critical points are on this interval, but if they were not, we would just cross them out and not consider them. So now I add these to my list. So I have x equals 8 and x equals -2. These are my critical points. So my global maximum and global minimum have to be obtained from one of these 4 x values. So for each one, I need to take that value and plug it back into the original function. You can totally do this on your calculator. That's what I did. So we're going to plug each one into the original function to see what the corresponding y value is. So when I plugged in -5, I get -58. When I plugged in 11, I got -234. When I plugged in 8, I get -396. And when I plugged in -2, I got 104. Okay. So once you have your list of y values, now you're considering where those y values are on a vertical axis. So which one is the highest and which one is the lowest. So here, the highest value is 104, which means that my global max, where am I going to write this? I guess we'll just write it right here. My global max is 104. Okay, that is the global maximum value. So again, your global values are the y values. Okay, unless the question asks you at what x value does this happen, your answer is the y value. Now for the global minimum, we have to think which one is the furthest down when we think about a number line that's vertical. And so when we look at these numbers, we're looking for the one that's most negative, since we have several negative numbers. So we get y equals 396. That is going to be our global minimum. And again, it's that y value that is the global minimum. Okay, so that's our process. We find endpoints, we find critical points, we make sure that our critical points are on the interval, then we plug all of those into the original and see what is our highest value and what is our lowest value. That's how we determine our global max and our global min. So we're going to try this with endpoints for a couple more problems just to get used to the process and to look at some functions that are a little bit trickier algebraically. But this is our first type, and this is the more common way that you're going to see it. So the next problem looks like this. The number h of eggs hatched by a specific insect is given Oh, at a given temperature T in degrees Celsius is given by H of T equals 2T cubed minus 45T squared plus 264T for T between 3 and 15. Find the temperature at which the largest number of eggs hatches. So different numbers of eggs hatch at different temperatures. Again, this is in Celsius, not Fahrenheit. So we're considering temperatures between 3 degrees Celsius and 15 degrees Celsius. And we want the largest number of eggs hatched. So we are looking for the global maximum here. And so again, it could be at one of these endpoints, 3 and 15, or one of the critical points. So we again will have to find critical points by using the first derivative and then taking those points to get values of the y variable, which here is h. We're going to plug our critical points and endpoints in here and see which gives us the largest number of hatches. Okay, so I'm going to give you 3 minutes again. Try this out. Start by finding the first derivative, find the critical points, make your list, and then see how many eggs we can hatch. What's the greatest number of eggs we can hatch? Okay, try that out. And in about 3 minutes, we'll go through it together. Okay, take about 30 more seconds. All right, so we start making a list with our endpoints. We have t equals 3 and t equals 15. And then to that list, we have to add any critical points that are on this interval. So to find our critical points, we're going to take the first derivative here. So we're gonna have 6t squared minus 90t plus 264. And we want to know, when does that equal 0? So I'm going to factor this, but again, if you use the quadratic equation, that's totally fine as well. So I have t squared minus 15t plus 44. And I did this by dividing everything by 6. I did it on my calculator, not in my head. I just have my notes over here. So I just went through, made sure everything was divisible by 6, and pulled that bad boy out. And so then I'm looking for two numbers that multiply to give me 44, but add up to give me 15. So I'm thinking 11 and 4. So here I have t minus 11 and t minus 4 equals 0. So that gives me two critical points, t equals 11, t equals 4. I want to make sure that they are both on my interval. So they certainly are between 3 and 15. So I can use both of them. So I have t equals 11 and t equals 4. So now I have my list, and I know that my global max and my global min has to happen when I plug in one of these values. So for each of these values, I'm going to plug them back into the original function. So when I plug a 3 back into the original function, I get 441 eggs hatched. When I plug a 15 back into the original function, I get 585 eggs hatched. When I plug in an 11, I get 121 eggs hatched. And when I plug in a 4, I get 464 eggs hatched. So I look at all of these numbers and they all make sense, right? The largest number of eggs hatched should all be positive. We can't really have negative eggs hatching. And I'm looking for the largest one, right? Because that's what the question asks, the largest number of eggs. So if I look at this list, the largest number here is 585. So this question says, find the temperature at which the largest number of eggs hatched. So for this one, I actually, once I find the global max, have to go back and find the associated temperature. So here, the solution would be that the temperature equals 15, and that gives us the global maximum, which is 585. Okay, so hopefully this process is starting to make sense. We're going to do one more like this that has the endpoints for us. The next one, the derivative is slightly trickier in the algebra, so we're going to try it out, and then we'll talk about some other ways we think about global maxes and mins. So here we want to find the global maximum of the function x over x squared plus 1 for the interval 0 to 2. So as you can imagine, we're going to have to do a quotient rule here. Not sure you can see that, so I'm going to write this slightly bigger. X over x squared plus 1 is our function. So we're going to do a quotient rule. And so from the quotient rule, we're going to be thinking, what are our critical points, right? And then we have our critical points and our two endpoints, which we're going to plug into the original to see which gives us the biggest value to find that global maximum. Okay, so again, take about 3 minutes, try it out. You know, if you have to look back at your quotient rule notes, that's totally fine. And then we will go through it together. Okay, take about 30 more seconds. Okay, so again, we start our list to include our endpoints. And then we go ahead and start finding our critical points. So here, to think about the first derivative, we do have to do a quotient rule. So our top function is going to be f, our bottom function is going to be g. Then we want to find each of their respective derivatives. The derivative of x is 1. The derivative of x squared plus 1 is going to be 2x. So then we're going to plug that into the quotient rule formula. So we're going to have f prime times g. So we have 1 times x squared plus 1 minus g prime times f, so 2x times x, divided by g squared. So x squared plus 1 squared. Okay, we want to simplify the numerator before we try to find anything, just to make our lives a little bit easier. So here we have x squared plus 1, and this is going to be minus 2x squared. Right? So we can simplify this and we get 1 minus x squared over x squared plus 1 squared. Okay, so for critical points, we are interested in when the first derivative equals 0 or where the first derivative is undefined. So we do have a denominator here. So we do need to consider if there's a value that will make this undefined. However, given that this is x squared plus 1, there's no value of x that will make this 0. So we don't even need to worry about the undefined case. So instead, we take the numerator and we set it equal to 0 to find those critical points. So let's bring the x squared over. We have 1 equals x squared. And we take the square root of both sides and we get x equals plus or minus 1. So the 2 points we have are x equals 1 and x equals negative 1. Okay. Now, before we can add these to our list, we need to make sure that they are on our interval. And what I notice is that negative 1 is not on this interval, right? The interval is 0 to 2. So negative 1 is not going to be added to my list because it's not on the given interval. So I'm only going to add x equals 1. Okay, so that's what happens when you check and something is on the interval, you just don't add it to your list. So now we're going to find our g value when we plug each of these back into the original. So we take 0, we plug it in, we get 0 over 0 plus 1. So 0 divided by 1 is 0. We plug in a 2, so we get 2 over 2 squared plus 1. So we have 2/5. And then we plug in a 1, we get 1 over 1 plus 1. We get 1/2. Okay, so here we are looking for just the global maximum. So we're just looking for the biggest value. So we look at these numbers to compare. We're looking for the biggest one. If you struggle with fractions and you're not sure how to compare them, you can turn them into decimals to figure out which one's bigger if you're not sure. Okay, not a big deal. So here we get g equals 1/2 is the biggest value of these on an interval. So our global maximum here equals 1/2. And so I can't stress this enough that the global maximum is the dependent value, the y value, or in this case, the g value. The number one thing students get wrong on a quiz is that you'll have something like this and I'll say, find the global maximum. And one of the answers will be 1, right? It'll say 1, 2/5, 1/2, 2, right? That'll be your list. And students will pick 1 because they forget that the global maximum is the dependent value. It's the 1/2. Okay, so make sure that you are reading the question carefully and answering it correctly. Okay, so the next sort of trial that we're going to go through is we're going to try to think about what we've learned about global maximums and minimums in relation to things like critical points and what we know about how functions behave. And we're going to do an analytical problem to see if we can figure out a couple different things. So we're going to do 2 analytical problems. This is the first of 2. So here, let g of x be a continuous function that has exactly 1 critical point in the interval -3 to 2. Find the x values at which the global maximums and global minimums occur on this interval, given that g prime of -2 equals 0 and g double prime of -2 equals 3. So in this problem, you really need to think about how we can use this information to answer the question. There's sort of a lot of information that we're compiling here that we need to think about. So I want you to take 2 minutes, see if you can figure out, what you know about this function. You might want to try graphing it. That might help. And see if you can then use that to figure out where the global max and min need to happen. Okay, take about 30 more seconds. Okay. So here, we're really trying to think about what we know, how we can apply it, and how we can answer the question. So the key piece of information here, there's exactly 1 critical point, okay? We are also told that g prime of -2 equals 0, and we know by definition that that makes this a critical point. So the only critical point happens at -2. We also know something about the second derivative. And I want to remind you that the second derivative is going to tell us about the concavity. Since the second derivative is greater than 0, we know that our function is concave up. Okay, so we have a function that's concave up that has 1 critical point. So what does this function look like? Right, so we're considering what's happening on the interval -3 to 2. So -3, -2, -1, right? 1, 2, 3. So if it's concave up and there's 1 critical point, that means that that critical point is a local minimum, right? So maybe the function does something like this, but we're only considering what's happening on this half, okay? And so since it's going to be a local minimum, that means that the other endpoint of -3 has to be the other point that we're considering, because remember, we're only looking from -3 to -2. So our global maximum happens at -3, at x equals -3, because we're asking the question here, when does this occur? So we're looking for the x values in this one. And the global minimum happens at x equals -2. And so you might be thinking, how do you know what happens in between -3 and -2? So I offer you this. Let's pretend that we think some crazy things are happening. How do we make sure that they're not, right? So we know we have to be concave up at -2, but what if we do something crazy like this in between, right? And the reason we know that that doesn't happen is because we know that there's only one critical point. So if it were to have turned around or done anything in between, it would create more critical points. And we only have one critical point. So that means that when we are moving between these 2 points, we don't have anything that turns around, right? So we might have something that looks like this. Okay, so we know we're concave up, so we might change concavity, right? We might be concave down here, that's fine, that doesn't create another critical point, but it still holds true that the maximum value is at -3 and that the minimum value is going to be at -2. You might also think, hey, what if it's a straight line, right? So how do you know that it doesn't look like this? Well, it can't be a straight line because the second derivative tells us that we are concave up. So it's got to have a bend to it. Linear functions would have a second derivative of 0 because there's no bend. So that tells me it's got to bend. And in order for it to bend, that means it's got to have this general shape, most likely. Okay, so that's how I'm able to figure out that the global minimum has to happen at -2 and that the global maximum has to happen at -3. Okay, so let's look at one more analytical here, and we're going to do some graphical analysis. So given the graph below, I want you to find the global maximum and minimum for the following intervals. So each of these examples is a different interval you need to consider. And so again, the global max and global min is the y value. You're just approximating it. It doesn't have to be exact, but the general y value for the global max and global min, considering each of these intervals. So take about 2.5 minutes. Jot down for each interval, and then we will go through it together. Okay, take about 30 more seconds. Okay. So for part A, this first interval is the entire given interval. So -1 to 1.5, we're looking at this whole red line, and we're trying to determine what is the global max and the global min. So if we look for the highest point, that's right here, we come over, we're approximating where that is on the y-axis. So we'll say something like global max, approximately, let's see, I think it's a little bit lower here. I'm going to say 0.6. Oh, 1.6. Let's pass the one, huh? So 1.6. You might have said something like 1.7, 1.75, right? All of those are fine. We're just approximating what this y value is. And then the global minimum, we are looking for the lowest y value. So if you look at all these y values, the lowest one is at the end point where it hits the axis. So the global minimum will be 0, okay? But now when we shrink the interval, we're now considering what's going on between 0 and 1, okay? Which means 0 and 1, that we're looking at this little part right here, 0 to 1, okay? So the global max, when I look at these, looks like it happens in 2 places, here and here, but both of them get to this value of 1. So 1 is the highest y value on this little sort of shaded part of the function. And then the global min, this point right here, right, where we dip down. And so we'll call that, I don't know, 0.8, maybe you called it 0.7, something like that. But whatever you approximate this value to be should be based on this value from this little divot right here, okay? And then last but not least, part C, we are considering what's happening between negative 0.5 and positive 0.5. So that's going to be here to here. So I'm going to try to shade this. Actually, I'll make this a little bit longer so we can see the interval. So from here to here, okay? So the global max in this instance is going to be this high point that happens right here, which was the one that we approximated earlier. I called that 1.6. Again, you might have called it 1.7, 1.75, anything in that general range is good. And then the global minimum happens at this little divot that we approximated for part B, right? So this little low point is right where we cross at 0.05. And so that's approximately 0.8 as the height. So when you're given an interval, you need to make sure you restrict the function and just look at that interval that's given to find the global max and the global min, okay? So all of these examples are examples where we are considering what happens with endpoints. And the majority of the time, that is the case, that we will have some reference to endpoints that we will be able to work with. However, occasionally, we're going to come back to this definition, we get a situation where we don't have endpoints, okay? And so how do we deal with it if there's no endpoints? Does that mean we can't do it? No. So in order to find global maximums and minimums on an interval excluding endpoints, so there's no endpoints given, we compute the values of the function at all the critical points, and then we use a picture of the function, if there are more than one, to determine if any of them are global values. Okay, so if there's only one critical point, then that is a global value, and we can either use the first, second derivative test or original function to determine if it's a global max or a global min. Okay, so what would that look like, right? So if you have multiple critical points but no endpoints, you may have something that looks like this, right? So we end up with 3 critical points here, but only one of them is global, right? So that's why if you have multiple, we have to use the picture to determine which one's actually the global point. If you only have one critical point, that means your function either looks like this or looks like this, right? Some version of that. And so what we do is we use the picture or the first derivative test or the second derivative test to determine if that critical point is a global max or a global min, right? So we can use the same types of things we were looking at before, but we are no longer comparing in a list like we were before, okay? So if there's no endpoints, the approach is slightly different. Like I said, this doesn't happen as often. So let's look at an example of this. This one is it's a little complicated algebraically. This will be a good review of your algebra skills. So for time t greater than equal to 0 in days, the rate at which photosynthesis takes place in the leaf of a plant, represented by the rate at which oxygen is produced, is approximated by P of t equals 100 e to the negative 0.02 t minus e to the negative 0.1 t. So the question is, when is photosynthesis occurring the fastest? So we're looking for the global maximum, which is the fastest rate or highest rate. And the second part is, what is that rate? So we need to find the critical point of this function. And since the way this question is worded is when is it fastest, we are assuming that the critical point that we find here will be the global maximum. So we need to find the critical point, and we need to plug it back into the original to also find what the actual rate is. So when we do the derivatives here, we have to be really, really careful with the algebra, but we can solve this for t. There's only one t value once you've worked out the algebra. So I'm going to give you about 3.5 minutes to do this. So again, you're going to find the first derivative. You're going to set it equal to 0. You're going to try to solve for t. The hint that I will give you is that when you take the first derivative, you end up with 2 functions that have a t in them, and you need to use algebra to reduce it down to only have 1 t. So hopefully you remember that with exponents and bases, but if not, do your best to find the derivative. And if you are not able to solve it, maybe try graphing the original to see if you can figure out where that max is. And then we'll go through it together, like I said, in about 3.5 minutes. Okay, take about 30 more seconds. Okay, so let's go on this adventure. So we start off with the original function. I'm just going to copy it down here so that we can then line up our derivative. E to the negative 0.02t minus e to the negative 0.1t. Okay, so we want to take the first derivative of this function. And so we see we have a constant multiple here. So the 100 will multiply the derivative of what's inside. So the derivative of the first e function, we have negative 0.02 e to the negative 0.02t minus, and then when we take the derivative of the second function, we have negative 0.1 e to the negative 0.1t. Okay, so here we have to be a little bit careful about all the negatives and things that are happening. So I'm just going to take one step to just simplify as we go. There's 0.02 e to the negative 0.02t. And now here we have minus a negative. So that's going to become plus 0.1 e to the negative 0.1t. It's really easy to get lost in the decimals of this problem, so try to be extra careful. We want to know, when does that equal 0? So we have two factors, this one and this one, equals 0. Well, we know that 100 doesn't equal 0. So that means the stuff that's in the parentheses would have to equal 0. So I'm just going to pull the stuff from the parentheses out. Okay. And this is where things get a little complicated, right? This is really where we're like, okay, what do we do with this? How do we solve this, right? And again, what I want you to notice is that these powers are different, right? If they were the same, we could just combine them into one term. We could add the 0.1 and the negative 0.02 and make it a common term. But these have different powers, okay? So we have two terms here. And so the way that we need to approach this algebraically is we need to figure out how to simplify this so that we only have one term that has a t in it, okay? And there's several different ways you can do this from this point. So if you didn't do this exactly like I did, that's okay. So I'm going to bring this term to the other side, okay? So left on the left-hand side, I have 0.1 e to the negative 0.1t equals 0.02 e to the negative 0.02t, okay? The reason why I brought this term to the other side is so that both terms would be positive. You can definitely bring the other term to the other side and have them both be negative and still arrive at the same answer, but we need one term to be on one side and one term to be on the other side so that we can then look at dividing things out. So what does that look like? I want all my constants to be on one side and all my e terms to be on the other side. So my first step, okay, is that I'm going to divide both sides by 0.02. I decided to do this just because the numbers work out nicely. We could have also divided both sides by 0.1 and put the constants on the other side. Okay, that would be totally fine. So here On the right, this has a ratio of 1. And if you do on your calculator, if you do 0.1 divided by 0.02, or maybe you know this, that simplifies to 5. So we have 5e to the negative 0.1t equals, now this is a 1, so we don't need to write it, e to the negative 0.02t. So now I've combined my constants. Since I put my constants to the left, I'm going to bring my e terms to the right. So I'm going to divide both sides by e to the negative 0.1t. Okay, and again, if you divided the 0.1 instead, then you would divide the other way with e's. That's totally fine. So we know that this is going to be 1. That's a ratio of 1. So that's going to go away. So now what we have to do is figure out what we can do with this. And this is where hopefully your algebra kicked in. When you have the ratio of two functions that have the same base, you can subtract their powers to simplify. Okay, what does that mean? I'm going to show you an example that we do often that's a little bit simpler. If you have x to the 6th over x squared, that is x to the 4th. Why? Because you have 6 of these x's multiplied together on the top, 2 on the bottom. You cancel 2, and you're left with x to the 4 on top. The way that we generalize this is we take the top number minus the bottom number to simplify. We're going to do the same thing here. We're going to keep our e, but we're going to do the top power minus the bottom power. Okay, so if you do negative, well, I guess we'll just do it sort of as a sidebar, right? If we do negative 0.02t minus negative 0.1t, we're asking what does that simplify into? So notice that the minuses cancel, okay? And you have positive 0.1t and minus negative 0.02t. That's going to give you 0.08t. Okay, and you can double check that on your calculator if you're not comfortable dealing with a lot of decimals. Okay, so again, I subtracted the powers from here, top minus bottom, to get my new power here. Okay, so now that I've done all that algebra, I'm left with 5 equals e to the 0.08t. The reason why I wanted to do this step is because if I only have one t, I can now use natural logs to get that t out of the power. So I take the natural log of both sides. When I take the natural log of e to some power, that power comes down out front. We know that the natural log of e is just 1, and anything times 1 is itself. So to solve finally for t, I divide both sides by this decimal, and I get the natural log of 5 divided by 0.08. Okay, so this is an exact answer. If I wanted to approximate this into an integer, I would plug this into my calculator and I would round. So let's say we round to 2 decimal places. I get 20.11. So it's my approximation. So these two numbers are the equivalent when you are approximating. So this is the exact answer. This is the decimal approximation. So at time 20.11 hours is when this rate is the largest. So that's the first part of the question. Okay, so the question was, when is it occurring the fastest? At time equals 20.11. The second part of the question, what is that rate? So if we want to know what the actual rate is when we are occurring the fastest, we need to take our t and plug it back into the original function. So we're going to take that and we're going to plug it into the original function, which is this one up here. You're going to plug it in here and here. And when you do that, that's going to do, you're going to do that on your calculator. You're going to get 53.499. So this is the rate of photosynthesis. And this is time in, what was our time units? Oh, in days. So after 20.11 days, the rate of photosynthesis is the fastest, and the rate is 53.499. Okay. The algebra on this is not simple. And as I mentioned, if you weren't really sure what to do at this point, right, once you've taken the derivative, you could graph it to kind of see what's going on. And so if you were to graph it, I just want to show you, you get something that looks like this, right? So you can see the function up here. I plugged it all in. And you can see it's got this shape, and I'm just kind of tracing it. But if you go to the peak, the global max, which is what I'm looking for, you can see it's right around 21, right? And we see here that that is what we found algebraically, 20.11, that, you know, is confirmed by the graph. It's right about 20.11. And if you look at the y value is 53.49, right? That's really close. So this agrees with our mathematical work. So if you get stuck, right, you can always rely on a picture to help you figure out where to go. Okay. So that's an example of how we would do this without any endpoints being involved. Like I said, this one is a little bit more challenging algebraically, but definitely doable if we're careful about all of our steps. Okay, so we'll stop here. On Tuesday, we will pick up with applications, where we are looking for maximums and minimums in context of different things like business and science and chemistry, things like that. So have a good rest of your day, and I will see you all on Tuesday.